thanks for the nice introduction, and also thanks for the invitation. It's really a pleasure to be here and talk to you about stages of IceCube. And during my talk, we'll give you an overview of kind of the challenges that we have faced in building this giant neutrino detector at the South Pole and the results that we have achieved so far, and then give an outlook in the future, kind of predicting what we might find or might not find, and also how we can in the future improve the detector more. So this is, let's see. So this is also the outline of my talk. So first I'm going to talk about the neutrino as a messenger particle, then introduce the IceCube detector, present some highlights, and before concluding, talk a bit about some future plans that we have with the detector. Now at the beginning, let me go back 100 years. So this is a picture of Victor Haas doing some balloon experiments, and he actually took an electroscope in the upper atmosphere up to 5-kilometer height to measure the ionizing radiation. And he observed that there's an increase in ionizing radiation with the altitude, and thereby discovering the cosmic rays. And to this date, we actually have measured this energy spectrum of the high-energy cosmic rays much more precisely with high-res Auger fly's eye, as is shown here. But the two main questions still remain: where are these particles coming from, and what are the mechanisms in the universe that can actually accelerate particles to energies of 10 to the 18 electron volts or even higher? And at these very high energies, a single proton actually carries the equivalent energy of a fast tennis serve. So it's a really energetic single particle. Now, how do neutrinos enter this picture? So we observe these high-energy cosmic rays, but unfortunately, these particles also bend. Let me just show this here. Bend in the intergalactic magnetic fields, so that if we observe a high-energy proton on the Earth, we actually don't know where it's coming from. So only at very high energies, where the bending radius is very small, you can try to do some correlation with cosmic sources. But neutrinos actually are very nice, since they are weakly interacting particles, so they just travel straight to us and really give us an unobscured view of the cosmos. And at these high energy, or the sources of the high energy cosmic rays, where we expect that protons are accelerated, these particles will also interact with protons and gamma rays in the vicinity of these accelerators and produce pions. And if these pions then decay, they produce neutrinos. And thereby, if we observe high-energy neutrinos, we can also point back to the sources of the high-energy cosmic rays and thereby solve this long-standing mystery of the sources of the high-energy cosmic rays. Now, unfortunately, life is not so simple, because neutrinos are also generated naturally in the Earth's atmosphere, and this is shown in this picture here. So there's a high-energy cosmic ray entering the upper Earth atmosphere, producing a shower. In this shower, pions and kaons are created. These particles decay and also give us a continuous stream of neutrinos. So this is the background that we have to face if we want to discover or observe high-energy neutrinos of astrophysical origin. Now, let me remind you how we detect actually these neutrinos. And this is shown in this cartoon here. And for example, if we have a high-energy muon neutrino coming in here, interacting with the nuclei via charged current interaction, it can produce a high-energy muon, so in this case for the muon neutrino. And these muons can travel quite far distances. So for example, at TeV, a high-energy muon can travel roughly 5 kilometers through water or ice. And it travels with the speed of light, which is faster than the speed of light in the medium, thereby sending out a cone of Cherenkov light. And this Cherenkov radiation is a very characteristic radiation that we can then use to reconstruct how the muon actually travels through our detector medium. This of course means that we have to have a detector medium with good optical properties, and also we need to have a sensor array where we can detect these Cherenkov photons. Now this idea of detecting neutrinos through the Cherenkov light emission has been pursued by several experiments around the world, and let me just give you an overview here. And so these are all the optical neutrino telescopes that we have around the world, and I'm also mentioning, for example, the Super Kamiokande detector here just as an example. So it's normally not regarded a high energy neutrino telescope, but I would like to point out that so the Super Kamiokande detector is a 50 kiloton detector that was artificially built basically by excavating a cavity in the Kamioka mountain and instrumenting it with 12,000 photomultiplier tubes, so light sensors. And this size is roughly the largest size of a detector that you can build from scratch. So if you want to have larger detectors, and you will actually need quite large detectors since the neutrino has a very low interaction cross-section, so you need to compensate what the neutrino interacts in interaction cross-sections through the detector volume. So you want to build very large detectors. And if you want to do that, then you have to rely on a naturally occurring optical medium that has good optical properties. And the three solutions that people have thought so far is fresh water, so it's like in this Lake Baikal experiment in Siberia, ocean water in the Mediterranean Sea, and also ice here at the geographic South Pole. And all these experiments that are labeled here in cyan, in pink, are currently operating, and by far the largest detector is actually the IceCube neutrino telescope, which is located at the geographic South Pole, which has a volume of 1 gigaton. And this is actually a picture of the detector completion, and you can see there's also some champagne on ice here, so people were celebrating after the completion. Yeah. And let me introduce also the IceCube coloration. So the IceCube coloration consists out of 38 institutions from around the world with 250 physicists, mostly in the US and in Europe, but also we have collaborators in Asia and also Australia and New Zealand. Now, getting to the South Pole has always been a bit of a challenge, and today we still have to face a lot of difficulties in traveling through the South Pole, and I have put together like a little comparison like of the first travel to the South Pole 100 years ago by Amundsen and Scott, and nowadays, and you can see that you still progress through the same stages, more or less. Now then, when you get to the geographic South Pole, and this is an aerial view, we actually go there via airplane and then land on this skiway. The geographic South Pole is actually located here. This is the South Pole research station that has, for example, the quarters and facilities. And up here you can see also a temperature profile for the geographic South Pole, and you can see that at the moment here it starts warming up. Towards the end of October we are getting here to minus 30 degrees, so it's still quite cold. But at this moment the station already opened up, and during this period from end of October till mid-February, that's actually when the station is accessible and when scientists actually fly out to the South Pole to construct experiments there, and also the IceCube neutrino detector. Now, building this giant detector, and I will go into more detail in a moment, has has been quite a challenge, and many people actually thought it's also a mission impossible to build such a giant detector. And this is actually a picture here from a recent movie, Mission Impossible. And you see here, this is Tom Cruise hanging, or his stuntman probably hanging from the Burj Khalifa tower. And he is actually roughly 480 meters up in the air. And if you could see the IceCube detector, the footprint here, and then the detector size, it actually looks roughly like this. So the IceCube detector consists out of 86 strings of optical sensors. These optical strings are arranged in a hexagonal pattern that have an inter-string spacing of 125 meters, and then the optical sensors are spaced 17 meters apart. And this is like an example of such a sensor. Let me actually show it in more detail here. So this is a schematic view of the detector, and you can see you have this regular hexagonal pattern of 86 strings, 125 meters apart, and also in between we have actually 8 strings that are inserted inside this regular pattern to form a more densely instrumented array, which is called the deep core detector. And this deep core detector has a closer string spacing up to 40 meters apart, and also the vertical spacing is just 7 meters apart. So this denser spacing allows for lower energy threshold, and therefore, therefore the detection threshold for neutrinos with a full detector is roughly 100 GeV, while the detection threshold with the deep core detector is closer to 10 GeV. And the detector was constructed over 7 years, and each season we deployed like additional strings, and I'm pointing out here the footprint of the detector as it grows. So this was actually in the 3rd year. We had 22 strings deployed, then moved on to 40 strings. Next year 59, 79, and then 86 strings. And this 86 string detector was completed in January 2010. So the full detector is taking data now since May 2011. Now let's also have a look at the optical sensors that are the eyes of our detector. So these consist out of a 10-inch Hamamatsu PMT that's engulfed in this pressure sphere, together with some digitization electronics that digitize or that sample over a length of 400 nanoseconds in 128 bins. And you can see here such a waveform. So this basically forms our raw data. And these little peaks here at 5 millivolt, these correspond to a single photo electron, so a single photon that's detected by our detector. This is a picture of some module testing that we did, and you can see sort of the size here of such an optical sensor. Now the question, of course, is always how do we get actually these sensors in the eyes, and this is actually shown here in this animation. So we first use a fern drill, which is shown here, to drill down to the first 50 meters, and then use a hot water drill, which basically sprays out a jet of hot water that melts itself down to to a depth of 2.5 kilometers. And this drilling proceeds in less than 40 hours down to this 2.5 kilometers. And then once the hole is drilled, it's basically filled with water, and we are then lowering these strings of optical sensors down into the hole. And this is also shown on this picture here. And what's shown is basically the time after starting the deployment and the depth of this string. And you can see this little sawtooth pattern here, which basically means that we are putting the first optical sensor on the string, lowering the string down by 17 meters, and then attaching the next optical module to it and lowering it down. takes roughly 6 minutes to attach an optical sensor and then lowering it down. And after we have all 60 sensors attached, then the whole string gets deployed down to this 2.5 kilometer depth.
What is the plan for the detectors when the project's over?
Yeah, so the optical sensors will stay in the ice, so there's no way to retrieve them. Yeah. There's actually, the Antarctic Treaty demands actually that we should return all scientific equipment once the project is over, but we hope to get an exception there. So yeah. So this is how it goes down then in the hole. And also one thing that we do is, of course, measuring the ice properties. It's very important. And for 4 of the drill holes, we have used a device that's called we have used basically this device where we have a laser beam that shoots a light into the ice, and that the light is then scattered and then received near the bottom. And by that, we can measure kind of the scattering and absorption in the ice based on the delay time and on the intensity of the light that's returned. And you can see this is actually a pattern. This is as function of the depth, so this is going deeper. And these curves here actually shifted just to visualize it better. And you can see these little bumps here actually impurities in the ice, and we have this layer between 1,900 to 2,100 meters in which we have more absorption in the ice. So this is actually corresponds to a dust layer. And you also see like little peaks in here. These correspond to kind of volcanic eruptions when there was dust introduced. The geological age here is roughly 100,000 years down to this 2.5 kilometers. So this dust layer here really corresponds to a global change in wind patterns, so that there was more dust deposited. But we can actually, these little peaks you can correlate with volcanic eruptions. Now, understanding these ice layers is something very important, as you can see also here in this animation. So this is actually some actual event data. And what's shown here is an animation of IceCube events. And the color here indicates the time when an optical module was hit, and then the size of this blob here indicates like how much charge or how much light was deposited in such a module. And the animation basically visualizes it easier to what you're actually seeing. And you're seeing that there's something passing from the top to the bottom to the detector. And these are actually downgoing atmospheric muons that are raining down on the detector with a rate of roughly 2.5 kilohertz or something like this. And one thing that you can notice is that in between here, a lot of time, it looks like that there are some hits missing. And this is actually due to this dust layer, which has a higher absorption, so the light gets absorbed there. So it's very important to actually understanding these ice layers precisely. Now, we are observing a lot of these events, these downgoing atmospheric muons. What we are actually interested in is observing events like these, where we actually observe a neutrino event. And the easiest to identify a neutrino event over a downgoing muon event is simply by looking for an upgoing event. So this is a neutrino comes in, interacts somewhere below the IceCube detector, and then produces a high energy muon that is upgoing. Unfortunately there, you also have background from atmospheric neutrinos, as I mentioned earlier. So these are then from neutrinos that are created in cosmic ray air showers on the northern hemisphere. And just to give you a sense of scale, so we observe roughly 10 to the 11 downgoing atmospheric muons per year, roughly 100,000 neutrino events, and we are still looking for these high energy neutrinos of astrophysical origin. Now, let me talk about the science that we can do with this experiment. And the science is actually extremely broad. IceCube is really a multi-purpose experiment, and today during my talk I can only cover like a few selected topics during my talk, but I hope to give you like some good idea of what we can do. And for all these analysis that I show here, we have already some preliminary results. I'm just flipping some of the plots here, and then we'll go in some more details for some of these analysis. Now, the capabilities of IceCube are actually made possible by really the capability to detect neutrinos from 10 GeV range to up to PeV range and beyond. And also we can detect MeV burst neutrinos. So this would be from a supernova explosion through an increase in the overall count rate of our sensors, so the overall noise rate. And then in general we have two types of event classes. The first one is a muon event, which is just passing through the detector. So this is what you saw in the previous animation also. But we also can observe a cascade-like event. So this is if an electron or tau neutrino interacts via charge current interaction, it produces an electromagnetic shower that looks more like a more circular in our detector. Now let me first talk about downgoing muons and science that we can do with that. So first of all, this is our muon rate as a function of time. So this the peak always corresponds to the austral summer. So this is when the atmosphere is largest in extents, and therefore the pions and kaons have more time to decay, and therefore give us a larger muon rate. And you can see that this rate actually increases as we increase the detector size. So you can see the different steps here. And this is a full array now where we have counting rates of this 2.1 kilohertz. We can also use downgoing atmospheric muons to actually test our reconstruction algorithms. And in this first analysis, actually, we looked at the shadow of the moon. So this is shown down here. This is basically where we measure the a deficit of muons coming from the direction of the moon, and we have observed the moon with 12 sigma significance so far. And also we can use this as a systematic cross-check for our reconstruction, and which is also shown down here. So this is the angular resolution that we achieve. So up by about the TeV, we have an angular resolution of about a degree, and if you go to higher energies, it actually further improves. And also one thing that we have studied with these downgoing muons is looking for an anisotropy in the muon flux, which is shown here, and we actually observe such an anisotropy. So this is basically mapping the neutrinos, the muons, which actually correlate with the direction of the high energy cosmic rays onto a sky map, and we are seeing basically a deficit in this region and some additional excess. Thank you. Some excess in this region. This is for a median energy of 20 TeV. The energy distribution is actually shown of these events. Is shown here, and we have a second analysis where we look at a higher median energy, and you can actually see that this excess and deficit are actually shifted, and this still remains a big mystery. And just recently, as you might have seen on Monday, we had a new paper on the archive where we actually extended this analysis also using the IceTop array, which is an air shower array located on the top of the IceCube detector. With this array, we can also access higher energies, and we went up to an energy of 1 PeV, which is and observed that this this anisotropy continues and even increases in magnitude. So this is something that's still a big mystery what's causing this. So, yeah.
Are these stripes in right ascension?
Yeah, these are stripes in right ascension, so this way basically, yeah. Now another big search that we are of course performing are the search for neutrinos from astrophysical sources. And there are basically 3 different ways how we can look for neutrinos of astrophysical origin. The first one, and since we are dominated really by downgoing atmospheric muons and then also the atmospheric neutrinos, we have to use statistical methods to really identify sources of astrophysical neutrinos. And so the first one that you can do is just mapping all these neutrinos that we observe on a sky map and looking if there is an excess from a certain direction. Then we can look for some time coincidence. For example, if there is some clustering, and especially in particular if this clustering is coming in coincidence with another event like a gamma ray burst or so basically looking for a transient source. Or we can try to reconstruct the neutrino energy spectrum and see if there's any change in this spectrum. And this is shown here. So from the atmospheric neutrinos, we expect a very steeply falling spectrum, which has a spectral index of roughly 3.7. So it's very steeply falling. And from astrophysical neutrinos, we expect a flux that's closer to e to the minus 2. So you would, if you go to higher energies, you would expect to observe a change in a spectral break in the spectrum. Now, let me start with the first analysis, which is the search for point sources. And I'm showing actually here the sky as it is observed in neutrinos for using this 40-string and 59-string detector. And I'm using this array actually because if we go to higher or to larger data set, this whole map is basically full of dots, so you cannot really see anything anymore. And we have used this to look for any excess, and the hottest spot that's actually observed sits right here. And if we just compare this to random maps, so if we scramble the sky map and then compute how often do you get like a higher significance in a scrambled map, then you get the following distribution. And so you can see that this observed value is well consistent with just a scrambled map. So actually in 67% of the cases, you would get a more extreme outcome. So this p-value of this hottest spot is actually not significant. We recently also unblinded another analysis that used 3 years of data, and also in there you can find that this p-value is 60%, so it's still consistent with just being random or random. Yeah. Now we also looked for coincidences, for example coincidence neutrinos with GRBs, and this is an analysis that used 2 years of data, and roughly 200 GRBs were sampled. Like in the first year, there's 117 gamma ray bursts, and in the second year, then 98 gamma ray bursts from the northern sky, and also in addition from southern sky. And we observed 0 events, and we should have expected, like from optimistic gamma ray burst models, up to 84 events, and therefore we were able to actually constrain these gamma ray burst models. We also looked for diffuse neutrino fluxes, which is shown up here. And here what's actually plotted is the EDX, which is the energy loss of the muon that passes through the detector which is sort of an energy estimator of these events. And you can see on this plot in blue, it's actually the expected background from atmospheric muons and atmospheric neutrinos. And then in these red lines, you can see what you expect from, for example, astrophysical neutrino fluxes. And you can see that in black, which are actually the data or the observed events, we have a few outlier events, so that in this analysis you can already see that maybe something starts to show up in this diffuse fluxes. And this is actually just setting the limit here as function of the energy, the flux limit. So this is the expected atmospheric neutrino spectrum, and these are the current upper limit, and this was the sensitivity of that analysis. Now in another analysis, we actually looked for electron neutrino events, and we observed in this analysis 3 candidate events at an energy of roughly, this is like 100 TeV, and these events are shown here. These are actually cascade-like events, so they are electron neutrinos, and they are also quite inconsistent actually with coming from just atmospheric neutrino fluxes. So in this analysis also we had an 1.6 sigma excess. So at this point it's not significant yet, but we start to maybe see hints of something. Also in a third analysis, which we just recently unblinded, so this is actually a search for GZK neutrinos, and these GZK neutrinos are actually, or Greisen-Satzman-Kutzmann neutrinos, are neutrinos that are generated when high energy cosmic rays interact resonantly with the cosmic microwave background, producing a delta resonance. This delta decays and gives you pions. These pions decay and give you these high energy neutrinos. So this GZK basic mechanism basically leads to a cutoff of the high energy cosmic ray spectrum. This is something that has been observed or hinted at in air shower radar, and we are also looking for these neutrinos basically that are produced in this mechanism. Now what we actually observed is, so from GZK neutrino models you expect something like this typically, that you have events at this 10 to the 6 or 10 to the 7 so this is number of photoelectrons, so this is our energy estimator, but you expect events in the EV range actually, and what we actually observed are 2 events, and this is more towards the low energy, so this is the number of photoelectrons that were observed in the detector, and these events correspond to an energy of 1.1 and 1.3 PeV. So these are the highest energy events that we have observed so far, and they are quite inconsistent with coming from atmospheric neutrino fluxes. So this is also something that so far has a significance of this 2.9 sigma, but it's starting to getting more interesting. Next, I want to talk also about some searches for dark matter. So this really shows that the IceCube detector is really a multi-purpose experiment. We can do other things that, we can do a variety of physics, including particle physics, so search for dark matter. And what I'm showing here is an edge-on view of a Milky Way type galaxy, and just to make it a bit better visible, I'm inverting this picture here. And if you could make dark matter visible, then you expect it to be somewhat distributed like this red color here. And this is something that you get from n-body simulations. So from dark matter simulations, you can get ideas basically how the dark matter is distributed in a Milky Way type galaxy. And what's plotted here is the dark matter density as a function of the distance from the galactic center, and for a variety of different profiles here, so which describes the dark matter density distribution. Now the Earth is located roughly at 8 kiloparsecs from the galactic center, and then if dark matter annihilates, we expect that it produces these all kind of standard model particles. These standard model particles can then decay and give us neutrinos, which we can look for. Now the situation that's shown on this schematic view here is pretty much what we're actually facing in real life. So we have the South Pole here, but the galactic center is actually roughly 30 degrees above the horizon. So if we want to look directly at the galactic center, we have to face also a large background of downgoing atmospheric muons. So in the easiest way, or to look for an dark matter, we can, and if we want to use the neutrino sample, we can look at the upgoing events. This is our cleanest sample. So we can, instead of looking directly at the galactic center, we can look close to it. So in the direction of the galactic center, and we can compare it with an off-source region, so looking for an anisotropy in the upgoing event sample. As the detector gets larger, or during the construction period, we can also start looking for starting events in the detector. So this, and that way we can also look at the galactic center. So these are then events that come from where dark matter annihilates near the galactic center, and then the neutrino actually interacts in the detector, and thereby we can reduce the downgoing atmospheric muon background. And we can also look for like these clumps here, which should represent like dwarf spheroidal galaxies. And we have done all these searches basically, and I'm just listing some references here before going in some details here. So the basic idea here is that you have the dark matter distribution, and we actually perform a line of sight integral. So this is integrating over the dark matter density squared along the line of sight, which gives you what's often called a J factor, which is the gives you the magnitude of the amount of annihilations that can happen. Then from particle physics, we know the neutrino spectra that are created if dark matter annihilates in a certain way, and we can then probe the dark matter self-annihilation cross-section as function of the WIMP mass. So the WIMP mass actually comes in here as a scaling of the dark matter density as the annihilation is proportional to the number density. And then we observe the neutrino flux. So in this first analysis, we are looking in the upgoing event sample. The galactic center is below the horizon, so it's harder to observe, and we're just looking at the upgoing events. And if there were dark matter self-annihilations, you would expect some anisotropy in the sky. So this is sort of shown by this blue color, or the intensity of the blue color. And we can then compare these two different regions here. And you can see that we actually, the number of events that we observed are compatible with each other, so we didn't observe any indication here of dark matter. Then in the second analysis, we looked directly at the galactic center, and now we are using this method where we are looking actually for starting events in the detector. So the neutrino comes in, interacts in the detector, and then produces a high energy muon, and we point this muon back to its origin, and thereby we can reduce this downgoing atmospheric muon background. Nevertheless, we are still dominated by downgoing muon background, so that's why this number of observed events here is so large. So this is actually, you see, we have this close to 800,000 events predicted from an off-source region and an on-source region, which is the galactic center, an 8 by 8 degree box around it. We observe this close to 800,000 events. Both numbers are consistent with each other, and we can proceed to set limits on the dark matter self-annihilation cross-section. So to put it in perspective here, this is sort of the plot, or the money plot. So as function of the dark matter mass, we have the self-annihilation cross-section, and everything above here is excluded. And what's shown here is this red line is from the Fermi Gamma Ray telescope, or Fermi-LAT, and this cyan line is from the MAGIC, which is the imaging Ash-Renkov telescope, also looking for gamma rays, and this line here is for HESS, also an imaging Ash-Renkov telescope. And this green area here is a model that's motivated by a positron excess that has been observed by a Pamela satellite that's actually shown here. So this positron excess has stirred a lot of interest in dark matter models motivated by this excess, because this is sort of exactly what you would expect if dark matter annihilates, and then you would expect such an increase. And if you, for example, explain this excess here with dark matter annihilating into tau tau, then you get this region. And up here are shown now the limits that we received or that we obtained with IceCube, and you can see that these already exclude some of the parameter space. So this is something I think a great success already, that we can probe these models. And another thing that you sort of see on this plot is the limits in gamma rays. They have a scaling roughly as 1 over n. So as you go to higher and higher density or higher and higher energies, the number density decreases, while the effective area of the gamma ray telescopes stays the same. So you get this 1 over n square scaling here actually with number density. For neutrinos, you have a benefit that the interaction cross-section increases with energy, and also the muon range. So therefore, these muon or the neutrino limits roughly stay flat. So at higher energies, the neutrino limits actually become better than the gamma ray constraints. Now, dark matter could also be captured actually in the sun. And the idea is the following here, that dark matter particle comes in, scatters off a nuclei in the sun, thereby loses some energy, and then sinks to the center of the sun, where it then starts accumulating. And if you have a bunch or a clump of dark matter near the center of the sun, it will start to annihilate, and the only particles that then can make it out of the sun are neutrinos. And as the sun accumulates more and more dark matter, the annihilation rate will increase, and it will increase up to a point where it becomes equal to the capture rate. And at this point where it's equal to the capture rate, there's another factor of 2 that you actually get, because you need 2 particles for an annihilation process, while the capture process is for a single particle. But once these two, the capture rate and annihilation rate, are in equilibrium, the neutrino flux from the sun only depends on the process that initiates the capture. So it's independent of the self-annihilation cross-section, which allows us to probe basically this initial process, which is the WIMP nucleon scattering. And actually, neutrino telescopes can set very competitive bounds here, and this is shown here. And you have, as function of the WIMP mass, we have the WIMP nucleon scattering cross-section here. And this is up here, and these dotted lines are from direct detection experiments on Earth, where you're basically looking for a nuclear recoil in these dark matter searches. And these red lines are the limits from IceCube. And as we don't know how dark matter annihilates, we are sort of assuming 2 extreme cases here. In the first case, dark matter annihilates into BB bar, which gives you a soft neutrino spectrum, so the limit is worse. And if you have annihilation into WW, it's a harder spectrum, so the limit is better. And you can see that these limits are already starting to probe this region. This is actually the region of interest. This is a region that you get if you look at supersymmetric models, so we can test these models. Oh. Yeah, sorry. Okay, let me also move on a bit into the future. So this latest result for the dark matter that's captured in the sun was particular. So we went down to very low dark matter masses, down to 20 GeV, and this is only made possible by this deep core detector, which is in the central part of the IceCube detector. And I showed earlier, so as a reminder, it consists out of these 8 strings that are inserted in between the IceCube regular 125 meter hexagonal pattern of strings, and has a lower energy threshold of roughly 10 GeV. And one of the things that we can do there is that we can look in particular well at starting events. So these are where the neutrino interacts directly in this detector, and we can use the surrounding IceCube detector to veto against downgoing atmospheric muons. So this is the idea is here, if you have a downgoing muon, it will produce hits in the IceCube detector, and therefore if you observe any such hits in the IceCube detector, you can veto such events. So your total detector volume is much smaller now, but you get a very clean neutrino sample from all directions. And one of the successes there with this detector has also been that we have observed an electron neutrino flux now that is consistent with coming from atmospheric, with the atmospheric electron neutrino flux, as is shown here. So these are 2 different models actually for neutrino production in the atmosphere, Bartol and Honda model, and our observation sort of falls right in between. So you observe a little bit more than 1,000 events, and these models predict something that's very close to that, and especially like a large fraction also of electron neutrinos. And you can also see, this is from simulation actually, the energy distribution of these events. Another thing that we have observed is also that these neutrinos oscillate in this range. So this is something that has been observed before, of course, by it's well known that the neutrinos oscillate, but it's a nice confirmation that we actually observe this effect now also with a neutrino telescope. So this is the first time that it was actually observed. Now for the future, we are planning to deploy even more strings inside the IceCube detector to form a more densely instrumented array. And this idea is called Pingu, which is a phased IceCube next generation upgrade, or precision IceCube next generation upgrade. And the idea is here, so this is a kind of a top view of the detector. These are the IceCube strings, these are the deep core strings, and we plan to deploy an additional 20 strings in between. And one of the nice things is really that the scattering length in the deep ice is close to 45 meters. So now the inter-string distance is shorter than the scattering length, so therefore you will receive a lot of direct unscattered light, which is most valuable in the event reconstruction. So first simulations have started for this detector. It's particularly interesting for studying dark matter neutrino oscillations, but also to observe galactic neutrino sources. And this is sort of some animation from events from simulation with IceCube only and with IceCube plus Pingu, and you can see that there, for the same event, there are many more hits, so you have a lot more information to actually reconstruct such events. It will have great prospects for dark matter searches, but also to study the neutrino mass hierarchy. And in addition, we also, for this Pingu detector, we plan to deploy calibration devices that can be used to better understand the ice, and also some new photosensors that can lead the way to an even larger upgrade. And this is the idea of the mica detector. So this is something that's even further in the future. And there the idea is to instrument a volume of roughly a megaton with like these thousands of optical sensors that have these small 3-inch PMTs. Sensors could look like this basically, and this also gives you some directional information about the event. Now with this detector, there will be a lot of interesting physics also that we can do, study neutrino properties in more detail, dark matter searches, supernova neutrino detection, galactic neutrino sources, or maybe even reach down to proton decay limits. Now, so this is kind of an outlook. So before I end my talk, let's go back to the first question. So this is a picture of Victor Hess, who 100 years ago first observed cosmic rays in a really daring balloon experiment. And up to this date, Austrians are still doing like very extreme balloon experiments, but this is a bit with more questionable outcome. But so I think we are getting closer to solving this 100-year-old riddle of the origin of the high-energy cosmic rays, as I showed during my talk with IceCube. And so the IceCube detector is now completed and taking data. We have a 98% uptime, so we have a lot of good high-quality data. I've shown many preliminary results during my talk, so it shows kind of the diverse science program that's ongoing, and there's also great prospects for the future with the existing data or data that we are going to take, and also with future upgrades. So, thank you very much.